Why are ground wires brought down one by one? Can't they be connected as a single continuous wire? Take a simple transformer stand as an example. It has multiple ground wires on top. Although it may seem like these ground wires are simply brought down from the top and connected to the ground pole below, each ground wire actually serves a specific purpose, representing a different grounding method. For instance, the ground wire that originates from the neutral point of the transformer serves as the grounding wire for the entire low-voltage power supply system. This is what we call system grounding or operational grounding. Without this ground wire, the system cannot function properly in its three-phase, four-wire configuration. Another example is the ground wire that connects to the metal shell of the transformer and the one connected to the distribution cabinet below. These wires fall into the category of protective grounding. The purpose of grounding the equipment's metal shell is to prevent accidental situations where the shell may become charged. By connecting these metal shells to the grounding wire, it provides a level of protection in case someone accidentally comes into contact with the charged shell. Additionally, there are also grounding wires for the 10 kV system. Lightning arresters are installed on the 10 kV power lines, and they are also connected to separate grounding wires. Now, you may wonder, can't we save costs by connecting all these ground wires together and then grounding them collectively? Or, if we want to ensure that the grounding resistance meets the standard, can't we just use thicker ground wires? Theoretically, reducing resistance by increasing the wire's cross-sectional area seems logical. However, in terms of electromagnetic compatibility, our primary concern is impedance. To effectively reduce impedance, the best approach is to increase the number of grounding wires. By connecting multiple grounding wires in parallel, we can achieve a lower grounding impedance. This is because when two wires are far apart, their mutual inductance decreases, and the total inductance is equivalent to half of a single wire. Hence, our grounding grid is constructed using multiple flat conductors that are positioned far apart. In the realm of electronics, when it comes to circuit boards, we usually create a ground network on double-layer boards. This practice effectively reduces ground impedance. Similarly, in multi-layer boards, dedicating an entire layer to grounding also helps minimize impedance. Ultimately, reliable grounding is an essential aspect of safe and dependable electrical systems. However, in the field of electronics, engineers are particularly concerned with electromagnetic compatibility issues related to low-voltage circuits. One crucial component of electromagnetic compatibility is electromagnetic shielding. In our subsequent discussions, we will delve deeper into grounding issues in the domain of electronics.